Hello everybody, this is lesson 1 of our solubility booklet. This is a remake of a lesson that we did in the Google Meet. So if you'd like to see these lessons made live, then please join us in the meetings that are held during class time. Otherwise, I'm going to go through a quick redo of that lesson because the recording did not work out. So we have a couple of extra little bits already written for us, but hopefully that's going to be okay for you. So the precipitation reactions is when we're talking about a equilibrium that has to do with solids going into liquid. So we're really going to be focusing in on the idea of aqueous. So aqueous reactions. Aqueous reactions are those that have some sort of solid dissolved in water. And this dissolving in water, that really implies concentration. And we know that concentration is related to rate. If concentration is related to rate, then there is a rate law. If there's a rate law, there might be a reverse reaction. If the reaction is reversible, then you have a case for an equilibrium. So aqueous solutions of ionic compounds is a subject that we covered in grade 11 chemistry. So in that chemistry, we would have talked about water, and water is a very unique molecule. It's not like incredibly unique, but it is actually, well, you know, it might be the most unique molecule. I mean, even compared to something like hydrogen sulfide, which is it's very similar in terms of atom structure, H2S, because it has a much higher, much lower boiling point. It's not nearly as exciting as water, which is liquid at room temperature. So water is, you know, the chemical of life and all that sort of stuff, and all of that really comes from a property called a dipole moment. So with water, we have oxygen, which is highly electronegative, and we have hydrogen, which is only moderately electronegative. And this difference in electronegativity grants a dipole moment, a partial positive charge on the hydrogen and a partial negative charge on the oxygen. In this case, doubled down because there's two hydrogen-oxygen bonds. And there's this little weird angle that happens, 104.5 degrees. If you go on to university, you'll learn a lot more about that 104.5 degrees and why that's a special number. But what happens here is that in each bond, we can draw what is known as a dipole moment. I'm going to pick a different color. How about green? So the dipole moment starts at the positive end, and it goes towards the negative element. And those can be drawn for each bond. And when you combine them, like you do in vector addition, you will get an overall bond, an overall vector, or an overall dipole moment, which we can see I've drawn out ahead of time here. And these dipole moments love to hang out with each other. They're kind of like, they kind of make this into sort of a bar magnet. So you can kind of think of it as like a negative end and a positive end. And so these little bar magnets love to be organized around each other. So another water molecule will come by and it'll organize itself such that it's connected near that positive end of the dipole. And in the case of hydrogen, this dipole interaction is so strong that the hydrogen itself can dislodge from the oxygen, and that can even form something called a hydronium, which is an H3O positive. It can even, and when that detaches, you can get a hydroxide. So that hydrogen mobility due to the dipole, that is what is known as if it's just a dipole, then it's a dipole-dipole interaction. Dipole interaction. And this is a force. This can be thought of as an intermolecular force. This is an intermolecular So between two forces, between two molecules, intermolecular force. And as with all forces, like the Coulomb force, it's something that needs to be overcome in order for chemical change to occur. Remember, chemical change is really just a rearrangement of atoms, and so forces in general oppose rearrangement. So this intermolecular force keeps things arranged as is, and they must be overcome if we want to change the chemicals. So this intermolecular force is a dipole-dipole interaction, specifically a specific type of that dipole interaction known as a hydrogen bond. Specifically, or additionally maybe, H bonding. And H bonding is a subclass of this dipole-dipole interaction. It relates to the positively charged hydrogens finding a certain attraction to oxygen, fluorine, or sulfur. Those are the only three elements that usually are considered able to form hydrogen bonds. And in this case, you have a bunch of oxygens, and oxygen is the best at hydrogen bonding. So these forces oppose change, and so we will occasionally have to compare those forces to other possible forces that can form. So, for example, the dipole moment of water. So I'm going to draw out my water molecule here. The dipole moment of a water, with its little dipole here, will also be attracted to ions. And in fact, this ion attraction is one of the most powerful forces that is found in chemical nature. So this interaction here, this little bit of force, let's put some like yellow force energy here. This is known as a dipole ion interaction. And it is generally, so this di is generally stronger than a simple dipole-dipole interaction. So this is one of the stronger forces. Sometimes, not always, it will depend on how many waters can get around an ion. So if we read this here, the ions, when dissolved in water, will become surrounded by water molecules. This is the dipole ion interaction, and become hydrated. This force of attraction between ions and dipoles is quite strong, and often will result in a much more favorable situation, a situation where the arrangement is energetically more stable because this force is so much stronger. And so these ions now are more freely moving as well. This gives us an additional bonus energy, because that will contribute to a concept called entropy or disorder. Now that these ions are free from their solid chains, they are able to move past each other, able to be mixed around, and they become disordered. And if you know anything about one of the laws of physics, is that the universe tends towards disorder. So changes in disorder are usually favorable. So what we're really looking at is in the case of a piece of solid molecule like this, like sodium chloride, before it is dropped into a liquid container, we have some ionic bonds that hold the ion together. We have some hydrogen bonding and dipole-dipole interactions, or intermolecular forces, that are holding, these are all intermolecular forces, so I just want to circle the whole thing. We have these intermolecular forces, the dipole-dipole and interactions, the hydrogen bonding that holds the water together, And then when that sodium chloride is put into the solution, you open up the possibility that the sodium and chlorine could engage in this dipole ion interaction, which is generally a stronger force than the dipole-dipole interaction by itself. Is it stronger than an ionic bond? That depends. Sometimes they are. or sometimes they're just comparable. And the stronger the interaction, the stronger the dipole-ion interaction relative to the strength of the ion bonds or ionic bonds, the more easily dissolved elements will go into water. Plus, you got that additional bonus from the entropy. So we lose the ionic bonds, which I've demonstrated here by crossing out the ionic bonds, but we gain this ion-dipole interaction. I called it dipole-ion a second ago, and ion-dipole, doesn't matter, which is a very strong intermolecular force. So the dipole-dipole energy and the hydrogen bonds are still there for water. Remember, there's a lot of water relative to dissolving a little bit of salt in it. So you have a lot of water, and you have some sort of, you get a change in energy. I don't know why I put a little arrow there. I'm not comfortable with that arrow. So you do have a change in energy, and you also have a change in entropy. The universe likes disorder, so the aqueous systems are naturally, I believe I got halfway through a thought here. Okay, the aqueous systems are naturally disordered, since compared to the order in solids. Okay, and so then, so the first thing we need to be able to do is write these dissociation equations. When writing a dissociation equation, you're going to take your ionic salt. You're going to think about identifying the metal and the non-metal that make up that salt, and then separating those out and remembering the charges that you would expect for each of them. If you don't remember the charges, they should be in your pink reference sheets, and so you can make reference to that sheet there. If the charge is still not there, you might have to figure it out by difference. So for example, when I look at sodium sulfate, I think that sodium metal is in the first column of the periodic table. So the first column of the periodic table means that it would have only a single electron, which it would lose to become an ion, single valence electron. So that means that sodium is a +1. The sulfate is going to act altogether as a single polyatomic ion, and that polyatomic ion will have to have a charge that balances these two sodium metal ions that are present. So that means that the total charge here is got to be a 2- on that sulfate, and that will balance out the overall chemical reaction here. And we can apply that to a bunch of these systems. Lead is one of the strange ones. So in this example, they gave us the label already. But remember that lead has two options. It could be lead 2 or lead 4. So you do have to read your words carefully. Same thing with iron. Iron is iron 3 chloride. So that means that iron has a 3+ charge. And so we need three different chlorine ions to balance it out. On the left and right, usually we need to have 0 charge. So our chemical formula has 0 charge on it, and then our ionic formula, or dissolved ionic formulas, have a negative and a positive charge. Please, please, please write your phases on the line. The phase symbols should be on the same line as your chemical symbols, and they should be in full script and in brackets with a small space after. Do not draw them as subscripts. I know that some teachers do subscripted symbols, but this is not in accordance with the IUPAC symbols, and so I do want to see that change. I learned it as subscripts when I was in high school, and then when I got to university, it was very embarrassing when I was in grad studies and I started writing these subscripted symbols, and my grad supervisor said, "What are you doing? You're a grad student. You should know that symbols go on the line." And I was like, "That's impossible. That's what they taught me in high school." And I went and looked up the IUPAC, and I realized that since I think like 1997 or something, it has been in like solid word that we were supposed to have them on the line. Maybe it was 2000, but still. So precipitates is the reverse of these reactions. Precipitate reactions are one type of aqueous reaction that is important in both nature and industry. The formation of structures in limestone caves and some gemstones are the result of precipitation reactions. Some very painful reactions might be like the formation, of kidney stones. So the formation of a kidney stone is a precipitation reaction, typically from from having a high salt diet without drinking enough water or keeping your fluids high enough. You can have the precipitation of salts inside your body, forming very painful crystals. So a precipitation reaction refers to the formation of insoluble salt when two solutions containing soluble salts are combined. And that is precipitation. I think of precipitation as anytime a salt forms, anytime a solution has been changed so that a salt is no longer soluble. That is precipitation. So it doesn't necessarily require the combination. I think actually this might be a misnomer here. Anytime, I'm actually going to type a little thing here. Anytime a solution is changed such that the dissolved molecules form a solid is referred to as a precipitation. So precipitation reaction, they are correct that I'm going to put this, there is literally no space on this page for my extra writing here, so I'm going to shrink it down a little bit. But a precipitation reaction particularly, a precipitation reaction is usually done by reacting two solvents together, or two dissolved solutions together. Maybe I can fit it. Oh yeah, look, there's a little bit of space up here. Okay. So a precipitation reaction is when we typically take two solutions and cause them to form a precipitate. The insoluble salt that falls out of solution is known as a precipitate. And this can happen in a couple of different ways. It doesn't require a reaction to do that. As I mentioned in the case of kidney stones really form because the person has a lack of water, and that lack of water causes the salt to be less soluble. But a precipitation reaction can also occur where you mix two solutions together. So these ionic salts are not very soluble in water because the attraction between the ions is greater than the attraction between the water and the individual ions. So what we're saying here is that in some cases the ionic bond strength is higher than the ion dipole interactions. So that's really what we're trying to say, as well as being higher than that entropy change. So even the increase in disorder is not enough to push that reaction to the dissolved state. So you can do a lot of different reactions. Silver nitrate and sodium chloride can be mixed together, and the result will be a little cloudy precipitate that's formed from these little crusty solids that form up, little solid crystals. A really nice looking reaction is when you take lead nitrate, which is a clear solution, and sodium chloride, also a clear solution. And I guess now that I'm here, I might as well fix this mistake I made earlier. If you take those two solutions and mix them together, you get what's sometimes referred to as yellow rain, the yellow rain experiment. You get this yellow precipitate that instantaneously forms. And you can do this holding the two jars in the air, and you can actually have them form this yellow precipitate while falling into a beaker. The reaction is incredibly quick, effectively instantaneous. As soon as the two solutions touch, the lead chloride solid will fall out of solution. So there's some things that happen here. I did a little bit of work here with the sodium chloride to try to justify it with some of the things we've discussed in our class before. So sodium ion has a 227 picometer radius, and silver ions have a 172 picometer radius. So when we compare the radiuses of sodium to silver chloride, we can say that the radial difference between the two is smaller. Remember that force of Coulomb's force is equal to some sort of constant times the charges divided by the radius squared. So the force is essentially proportional to the square of the radius. So if the value goes down, you get a huge benefit in the force. So the Coulomb attraction is higher for silver chloride, and so then this will decrease the solubility of sodium chloride. On the other side of things, not only is the ionic force, remember that we're trying to say that it's the comparison of ionic bonding to the dipole ion interaction. Well, sodium, by being a little bit bigger, you can actually get more waters. So you can get more waters around the atom compared to the silver ion, which is smaller. So the silver ion will have less waters around it. This is more of these ion dipole interactions, right? These are these ID interactions, or whatever, DI interactions. And so we have less of them for the silver because the silver ion is smaller. So the smaller ions equal, so we can kind of say, smaller ions equal a higher force, Coulomb, and less ion dipole interactions. We will also find that higher charged ions also have this have a higher force as well. So you'll find that things like magnesium will have less solubility than sodium. So with that in mind, anything that's not dissolved in these reactions is known as a spectator ion. So we'll identify those in a little bit when we start talking about the reactions. But these little observations about ions, about force, the Coulomb attraction, the ionic bond force versus the ion dipole interaction, and that sort of thing, can actually be visualized in an empirical set of rules. And by empirical, I mean that they're good rules of thumb. That's why I put little dashes on them, but they aren't guaranteed. But they are very effective for most situations you'll come across. So, for example, all of the single-charged elements in the first column of the periodic table, these are all the biggest elements in that row, and they also have a very small charge. So these all end up becoming water soluble. So these are all large, all big ions with low charge. So that's usually a good sign that that big ion is going to give you lots of dipole ion interactions. That low charge is going to give you a weak ionic bond. Similar idea with the chlorides, bromides, and iodides. They all have fairly strong ion dipole interactions. They are a little bit on the small side, but they tend to form very nice bonding with hydrogen because of reasons, I guess. They're very some of them can even form sort of pseudo hydrogen bonding. But if they're combined with elements that have a similar size or high charge, like mercury, or lead, or silver and copper, which have similar sizes to them, they end up having very strong ionic bonds with those elements. Very large counter ions, like the sodium nitrate, tends to be very soluble, or the acetate, and also a very large molecule, because those large molecules can get lots of waters around them when they're dissolved. You don't need to know the reasons. You can just learn these rules, and these rules are actually even provided for you on the exam in a table of rules. Sulfates are water soluble, again, because they're very large. There are some exceptions. There are some molecules like sulfides, which are water insoluble, and that's more or less because sulfur has a high charge and it's a little bit big, or a little bit small for its high charge, so it tends to form pretty strong bonds. Hydroxides are typically insoluble because oxygen is fairly a small element, and so it does bond very strongly. Meanwhile, the carbonates and the phosphates and sulfites are also very symmetrical, big symmetrical elements that tend to be insoluble. I don't have a really good reason for that one. It's just something you have to learn. So how can we use that? Well, I'll show you a couple of examples. Maybe I will, you know what, I'll clear this page and we can do this page together. So let's just do that. So we can use these rules by looking at things like this. So here we are looking at a sodium sulfate, and we want to find out if it's soluble. And the first thing I see is I see a sodium, and I say, wait a second, all group 1 elements are soluble. So I don't have to go any farther than that. As soon as I satisfy a rule that does not have an expectation and does not have an exception, then that includes the other counterion, then I can go for it. So here I can see that there's only one exception in that first rule, and this is definitely not it. So we say soluble. If it's silver nitrate, I also know that all nitrates are soluble, so that's also soluble. In the case of aluminum hydroxide, I recognize the word hydroxide as one of my rules. So let's go see what that hydroxide rule says. It's right here. It says all hydroxides are water insoluble except for main group 1 and compounds of hydrogen, strontium, barium, and ammonia. Well, that's not ammonia, strontium, or barium, so this is insoluble. Lead chloride, okay. Chlorine is generally soluble, but I better check that rule because lead is a pretty positive ion. And I see right here, there's my trick, is that lead is one of the exceptions. So lead chloride is insoluble. Potassium bromide, again, we got that K over here. So that is that first group, so that is always soluble. And in fact, the second part of it is also soluble. Chlorides are generally soluble, but I do see magnesium, and I know that magnesium is a 2+ ion. So it might be an exception. It has a high charge, so I got to worry about that. So let's go back. Chlorides, bromides, iodines are water soluble. Exceptions are not mercury. So for some reason, that's okay. So this is another soluble one. Maybe mercury is big enough to get some lots of waters around it. Iron 3 chloride is also in that same rule. So let's just double check to see if iron is one of the exceptions, and it is not. So that would also be soluble. Okay, so that's how we would do that question. So the next section is about precipitation reactions, and I will be covering that in the next class. So I'm going to leave that for today. Thanks.